All right, folks, let's do this. So we're doing systems, and I gave you a systems of linear equations problem a couple days ago. We're going to do something similar to that. Yeah, that could be valuable, or it could be worth $1. If you want to know, this information is used a lot in earthquakes, because earthquake. What am I trying to say here? Earthquakes travel at a pretty much a constant rate. Okay, they diminish over distance, but they travel at a constant rate. And if if they put up some seismic stations, okay, the seismic station will actually record the time that earthquake hits it. Okay, and what they can actually do is construct a possible radius of where that earthquake would occur from each station. So station 1, 2, and 3 would each get that earthquake. They would record it at different times. From that time data, they can figure out how far away from the epicenter that location is. And they draw a few circles of the system, and then where those circles intersect is where the epicenter of the earthquake is. You have to have 3 set pieces of data, and this is a system of equations. Okay, so based on those 3 items, you can calculate where the earthquake was. Okay, just a little aside there. These systems, what happens when they don't intersect? How many solutions are there? Yeah, there's no solutions. Okay. You could have 1 solution. What's the possible maximum amount of solutions with what we studied this last couple weeks? Infinite, yes. Thank you. Numerically, 700. Nice. Nice guess. Okay, you can have 2. What might 2 solutions look like? Okay, that's a good one. 2 solutions. Can you think of a situation where there are 3 solutions? With 2 equations. Thanks for the thought, though. Yeah. Cubic and what? That's 4. Hey, look at that. So, how about this? Oh, there's 4. Can you manipulate that picture to make 3? How? What? There we go. There's 3. Okay, so can you do one with 5? Sure, why not? Two graphs can they intersect in 5 places with just conic sections? Just conic sections.
So like parabola and stuff?
Yeah, parabola, hyperbola, ellipse, circle. The answer is no, right? You can do up to 4, like this one, but you can't do any more than that unless it's infinite. Infinite would mean it's the same one, right? Okay. What do you remember the problem with graphical systems is? What's the problem with doing a system graphically? Thank you, Taylor. It's not accurate. Okay, so if I do that circle, and that's an ellipse, correct? How many intersections and where are they? Yep, that's the trick. Okay, what's the circle? Okay, center 0, 0, radius 5. I'm gonna do this one in red. Okay, there's your circle. Put the ellipse in blue. Is this horizontal or vertical? Yeah, it's a horizontal because A is bigger. Okay, so A is 6 and B is 3. Do we need to figure out C to graph these? Yay, nay? No, the foci involves C. The vertices are A. So we go out 6. It's center 0, 0 again, right? Those are your A values and your B. Yeah, 4 solutions. What are the approximate locations of those? What's that point? 4, 2. Probably 4, -2, right? -4, -2, and -4, 2. Approximately, because my drawing is not perfect. So that's the graphical.
You'll have to be able to graph all these conic sections to do those. It is fabulous. You are correct. It's math. Doesn't get any better than this.
Pretty sure it is.
Like tonight when you beat Coleridge. Okay, algebraically, how would you solve this one? Any ideas? Couple ways. Anybody? Remember, we have two ways to do systems, right? Elimination or substitution. Which would you prefer? I agree. So how can we change one of these to make it look, one of the variables to look like x squared? What can I do to this to make it x squared? Well, thank you, Logan Olson. Multiply by 36. So we get x squared plus 4y squared equals 36. We still have the original circle. Don't get, the reason this is not a circle is because there's 4y squareds there. Okay. So be careful on those. Now you can subtract. You get negative 3y squared equals yeah, 36 divided by 9 is 4, right? Thanks for asking. So y is positive or negative square root of 11 over 3. So we have our y values. Is that close? Is that close to 2? What's 12 divided by 3? Leroy, 4. Square root of 4 is 2. So we're pretty close, right? So our y values are pretty close. The question is, what are our x values now? Yeah, you have to plug it in. And you have to plug each of those in separately. So you have positive version, and then you'll do the negative one later. This is x squared plus 11 over 3 equals. I changed that to thirds so I can subtract the fractions. It's 75 over 3. Well, this is 25 over 1. Multiply by 3, top and bottom. Subtract this over. Eight over root 3. Right. So what is our simplified? Yeah. So it's positive or negative 8 root 3 over 3, which is approximately 4.5-ish. Okay. Now, I just realized this, do I need to put the negative version in here? What's a negative squared? Positive. So it comes out anyway, so we don't need to worry about doing that again. We have all 4 of our points, so we just need to combine these in four ways. Put the positives together. Put the positive with the negative. Oh boy, you are so right. That's the y value. Scratch. Thanks for pointing that out. Who has not been getting enough sleep? All of us. Yeah, we got past that about 20 minutes ago. And all right, so those are our 4 points. Is there an easier way to write that? Yes. So we could do this as well. That's perfectly acceptable. Okay. There is no possible way for me to show you every problem you can encounter, because we'd be here for weeks. No, not fabulous. Okay. So I'm going to leave it there for today. We are going to work on this again Tuesday. It's not due until Wednesday. That does not mean do it Tuesday night. Yeah, well, you can do more than that if you want. Yeah, don't let me forget.